Okay, I said earlier in the revision session today that we'd go through question 3 from the summer 2021 paper, and then in a separate video I'll go through some of the bits from question 4 as well. So this is all dealing with this simple climate model where the temperature of the Earth in this case is given by this equation, the fourth root of 1 minus alpha multiplied by s all over 4 sigma. This is a constant, this is the output of the sun, this is the Earth's reflectivity, and this is the surface temperature. Now I went through the exercise of balancing the units on each side during the class, and you'll see that on the answers as well. But I just wanted to quickly go through some of the other bits. So the first part, question B, asks you to calculate what the temperature is, and really that's just a case of putting in the values that are given in the equation. Given in the question into the equation. So really it's just it's quite a complicated equation, I suppose. So 1 minus the 0.3, because that's the value you're given for alpha, times s, which is 1380 watts per meter squared, divided by 4 times 5.67 times 10 to the power of minus 8. Sorry, just looking at those at the same time. So you put that all in your calculator and you'll get a temperature out of 255.5 Kelvin. Okay, in question C, it asks you to work out, well, what would happen if you were to include an extra greenhouse gas term. And it says that the way of accounting for this greenhouse gas term is that we change this model up here by adding an n. Basically, we multiply this whole bit by n. So instead of it being this, it becomes t equals the fourth root of 1 minus alpha s times n. You could write that n anywhere, divided by 4 sigma. And then it also tells you that n equals 1.66. So then if we go through and then do the same thing with that calculation, except this time we've got n equals 1.66, we come out with a temperature of 290 Kelvin. And then the question for the last bit of the question, it asks you to tell you, well, what's the difference then between these two? Well, i.e. how much warmer is it when we account for the greenhouse effect? So this number minus this number here, difference is 34.5 Kelvin. Okay, that's pretty straightforward, I think. That's just questions B and C. On that, let's have now look at part D of this question. And D asks you, if the Earth is 10% more reflective, what would the greenhouse gas factor need to be in order to keep this the Earth's surface temperature unchanged? So let's just remind ourselves, we've got T equals this equation, fourth root of 1 minus alpha times n times s all over 4 sigma. So now instead of alpha normally is 0.3, which so that's the Earth's reflectivity, its albedo, that is the fraction of light essentially which just goes straight back out into space of sunlight coming in. So we're saying the Earth is 10% more reflective. So if it's 10% more reflective, instead of alpha being 0.3, alpha would become 0.4, i.e. 10% more of that light has gone back out to space. So it's gone from 30% more reflective to 40% reflective. Okay, so everything else is the same. So we want the temperature to be 290 Kelvin. Okay, so what we're saying is, well, what would this have to be in order for temperatures to be 290 Kelvin, but now alpha is 0.4. So let's rearrange this equation up here so we get n as the subject. So if we do both sides to the power 4, so t to the power 4 equals 1 minus alpha times n times s all over 4 sigma. Take the 4 sigma up here, t times 4 sigma equals 1 minus alpha n times s. So we've got the n by itself, so now if we divide both sides by 1 minus alpha s, we get n equals t times 4 sigma over 1 minus alpha s. Okay, and then it's just a case of putting the numbers in. So we've got 290 for here, 5.67 times 10 to the minus 8 for this, 1 minus alpha. So alpha is now 0.4, so 1 minus alpha becomes 0.6, and this is then times 1380. And then the answer that you get is 1.93. Okay, so that's that question done as well.